Okay, welcome to the course on biostatistics and design of experiments. We introduced a new distribution in the previous lecture. It is called the Weibull distribution. We will continue on that. Weibull is a very useful distribution. It gives you a reliability of a part, a biomaterial for example. It can be used in quality control. You are manufacturing some material. I want to know what is the failure rate. I want to know when each material will fail on average. So, it is time to failure data. So, how long it will take to fail. So, you can do this type of calculations. Okay. So, will it take 1 year, 2 years or more than that. There are 3 parameters in Weibull distribution function or Weibull probability density function. Beta, that is the shape, scale is the eta, and other one is the location or threshold gamma, and the probability density function looks like this. Okay. We can make gamma equal to 0. So, then it becomes a 2 parameter density function, beta and eta. Beta is your shape and eta is your scale. Both are non-negative, that means they cannot be, they are greater than 0. Okay. So, the shape parameter tells you how the curve looks like. Okay. Approximately around 3 the Weibull distribution, if beta is equal to 3, Weibull distribution looks like a normal distribution. If it is 1.25, it is sort of right skewed. If it is a large number like 10, it is left skewed. So, it is leaning towards the right hand side, leaning towards the left hand side. Then if you look at the probability, it is called the unreliability and the time here. Okay. So, for different values of beta, beta is equal to 1, goes like this. It is called the exponential distribution, that is constant failure rate, beta less than 1 like this, you know, decreasing failure rate, that is with time the failure rate goes down, and beta is greater than 1, let us say for beta equal to 3, increasing failure rate, that means failure rate will increase with time. Generally we will observe in many situations like this, actually failure rate keeps increasing with time because of wear, tear and so many other factors, age, we sometimes call it age, right. Because of the age, probability of the equipment failing also keeps going up and up. So, if you look at keeping beta constant, if you keep changing eta, okay, we see the graph gets pushed to the right. Okay. So, the mean value gets pushed to the right, and the peak also keeps going down. Okay. Okay. So, you can see this very clearly. So, the peak also goes down and the mean gets pushed to the right. So, larger the eta, okay, we are trying to prolong the failure rate, that is what it means actually. So, next one is the threshold, that is the eta. What eta does is it shifts the entire graph to the right hand side, I mean to the right. Okay, it shifts, as you can see. If gamma is equal to 0, the graph will start from the origin, whereas any other gamma, it will start from that particular place and go. Okay. So, gamma does only that, just shifts the whole thing. So, gamma has an units of time, your beta also has units of time. Okay, both are units of time. So, time could be hours or week or minutes or years and so on actually. So, a 2 parameter Weibull like 400 distribution is exactly same as a 3 parameter 430, where this 30 all it does is it shifts the graph from 0, that is the origin, into the 30th point. So, Weibull distribution is an alternate to the normal distribution in the case of skewed data. So, if you have a skewed data, then we can use Weibull distribution for that actually. And the exponential distribution is a special case of Weibull distribution, because exponential distribution we say beta is equal to 1, you have constant failure rate. Okay. Okay, gamma has the same units as time. Okay. it tells you gamma gives an estimate of the earliest time to failure. So, suppose if gamma is 10, then we can say your one of the parts will fail, it will start failing from the 10th hour. So, it is the earliest time for failure. So, a negative may indicate that failures have already occurred prior to the beginning of the test also, that is if gamma is negative. So, the graph is starting from some other place here, right, below the origin. So, obviously that means failures have already occurred before we start our test. Okay. So, these are the 3 parameters in Weibull distribution, and these are the meaning of these 3 parameters. Okay. We will look at some more terminologies. There is something called Weibull reliability function. Okay, it is given by this. Okay, Weibull reliability function e power minus t by gamma by eta raised to the beta, whereas as usual if I remove the threshold, put it as 0, okay, then you will end up having RT is equal to e power minus t by eta raised to the power beta. When do you use it? It can be used to derive reliability metrics such as reliability function, failure rate, mean, median, and that sort of situation. So, RT decreases for beta lying between 0 to 1. For beta is equal to 1, RT decreases monotonically like this with time. So, the reliability of any part will keep coming down with time. That is obvious, right? Even in your house you have light bulb, a new light bulb reliability is very high. After 1 or 2 years you are very scared because you think the bulb may fail. That is true even with your mobile phones, with any material. Okay. Generally the reliability will keep going down monotonically, but okay, when beta is equal to 1. When beta is greater than 1, okay, when if beta is greater than 1, the reliability decreases. Okay. Okay, so beta is greater than 1, so the reliability will beta is greater than RT decreases, and then it can also increase. So, if beta, if you have a beta is say 0.5, that is it is less than 1, so it goes down, but later on it sort of stabilizes. Okay. So, sometimes you see a very old television keeps working, after some time you will not know how long it has been working for. Okay. So, that could be beta is equal to this type of number, beta less than 0.1. Okay. Okay. There is another term which is called Weibull failure rate. Okay. It is called Weibull failure rate function. It is given like this: beta by eta t minus gamma divided by okay, eta raised to the power beta minus 1. Okay. So, in the previous case we looked at the reliability, which is given by this relationship. Okay. It is given by this relationship. Whereas this is Weibull failure rate, which is given by this relationship, failure rate function. So, it is a combination of Ft and Rt. Rt is your reliability function and Ft is your original Weibull distribution. So, Ft by Rt is your failure rate function, that is the failure rate function, that is failures per time as a function of time here. Okay. That is called the failure rate function. So, when beta less than 1, obviously it will keep going down and down and down like that. So, the failure rate will decrease with time. So, initially it may fail much more, failure rate is much higher, but after a very long time the failure rate is much lower actually. With beta is equal to 1, the failure rate is constant. This is called a constant failure rate. Beta is equal to 1, because when we put beta is equal to 1, this becomes 0. So, the whole term becomes 1. So, we have only beta divided by eta. So, beta is equal to 1. So, it goes like this. Okay. Now, if beta is equal greater than 1, then beta greater than 1, the here you have say beta is equal to 3 means this term becomes square. So, obviously, it takes up this type of shape. Okay. It is increasing dramatically, that means the failure rate increases with time. Okay. So, initially if you expect it to have a failure rate of something 2 per time, 2 per second or 2 per week or something, with time it may go dramatically very high. So, it may go from 2 failures per minute to 100 failures per minute, because you get a sharp increase in the failure rate. So, this is called the failure rate function. This is also very important, and the previous one is called the reliability function, how reliable the material is, RT. Okay. So, we can also calculate unreliable by subtracting this from 1. Whereas the previous one, this particular graph is called the Weibull 2 parameter or 3 parameter Weibull distribution function. Okay. Weibull distribution probability function. Okay. All these are useful when we start looking at problems, and then there is another term that is called the mean time to failure, MTTF, mean time to failure. Okay. What is the mean time? Like in clinical when you are doing a drug discovery, we say concentration at which 50% of the cancer cells die. What is, we call that as IC50. Concentration at which 50% of the bacterial growth is inhibited, we call it as IC50. Concentration at which 50% of the animals die, okay, we call it LD50, lethal dose 50. So, similar to that we can calculate also 50% life from this formula, but this particular equation gives you the mean time to failure. So, we have gamma, we have eta, we have beta, and so if you want to have see what is the failure rate, what is the failure for 50, then you end up having this type of relationship, right. Okay. Now, this is called average time, okay, mean time is equal to gamma plus eta. This is a gamma function, this is a gamma function, and the gamma function is defined like this: gamma n is equal to integral 0 to infinity e power minus x raised to the power n minus 1 dx. So, you do not have to get tense about it, because there is a table which gives you for. So, gamma 1 is 0 factorial, that is 1, gamma 2 is 1 factorial, that is 1, gamma 3 is 2 factorial, that is 2, gamma 4 is 3 factorial, that is 3 into 2 6, and so on. Actually gamma 0 is minus 1 factorial, which is infinity, gamma 1 is minus 2 factorial, again this is infinity, and so on actually. So, we can use this particular table and do our calculations. Okay. So, nothing to worry about it, because we are going to look at some problems also as we move along. Okay. There is an Excel function which is available, it is called Weibull x alpha beta cumulative. So, alpha and beta are the shape and scale parameters. Okay, here they use different names, shape and scale parameters. In our original problem we used shape and scale parameters beta and eta, but in Excel say you call it alpha beta. So, no problem. So, x is the value at which you want to calculate the Weibull, should be greater than or equal to 0. Cumulative, true or false. Okay. If you give it at false, then it gives you the value of the probability density function fx at x. If you give it as true, then it gives you the Weibull cumulative distribution function, okay, at x. So, if you give true, it gives cumulative, if you give false, it gives the actual value. Okay, we will look at some problems as we go along. So, we have defined quite a lot of terminologies here. One is called the mean time to failure, okay, and the other is called the Weibull failure rate function, and the other one is called the Weibull reliability function. Okay, okay, let us look at some problems, and that will make things much clearer. The time to failure of an artificial valve follows a Weibull distribution with scale is equal to 2000 and shape is equal to 0.5. Okay. Scale shape is 0.5, scale is 2000. Okay. So, what are they? Scale is eta, shape is beta. Okay. So, it is given as 2000 and 0.5. What is the probability that these artificial valves will last more than 4000 hours? Okay. And then what is the mean time to failure? So, the probability that the artificial valve will last no more than 4000 hours, we can calculate Weibull. X value is 4000, as you can see, the first is the shape, second is the scale. So, the shape is 0.5, scale is 2000, then if you give true, it gives you the total probability, okay, for failure. Okay. So, if you want to calculate probability that it lasts more than you have to subtract from 1. So, the probability is 24.3 minutes, sorry, 24.3%. So, probability that the screen will last more than 4000 hours is 0.243. So, let us look at the Excel function also. Okay, so we say Weibull, sorry, Weibull. So, first is we want to know what is the probability that it will last, probably the screen will last more than 4000 hours. So, 4000 is the first term, comma, the shape, you have to give the shape first, okay, and then you have to give the scale next, and then we are giving it as true because we want to get the total, that gives you 0.7563. So, the probability that the probability is given last. So, probability of failure for less than is given by this, because where the, if you look at the Weibull, okay, it gives you this value. Cumulative distribution. So, we want to know the lasting, that means we have to do 1 minus this. So, 1 minus this will give you 0.243, that means probability that these artificial valves will last at least 4000 hours is given by 0.243. Okay. What is the mean time to failure? Okay. How do you calculate? There is again a formula here. Mean time to failure is given by this formula, T is equal to gamma plus eta tau 1 by beta plus 1. Okay. So, we will say so we can give a 1 divided by 1 plus 0.5, this is the gamma function of this, and then this is the, where we will neglect this particular gamma here, okay, and then okay, we will put this, the 2000 here. So, 2000 into gamma of 1 plus 1 divided by 0.5. So, you need to remember that this beta is different from that beta, because this beta is different from our beta here actually. So, do not get confused that eta is same as this beta. So, what we will do is, so we have 2000 here, okay, and then gamma function, because it is given, the equation is given like this, okay. So, here we will neglect this small gamma. So, we will have this into gamma function of 1 by beta plus 1, okay, gamma function of 1 plus 1 divided by 0.5, okay, and as you know 1 plus 1 divided by 0.5 is nothing but okay, 2 plus 1 is 3. So, gamma of 3 is given by 2, and then on this side you have 2000. So, 2000 into 2 is 4000 hours. So, mean time to failure is 4000 hours actually. We can also use there is a command called gamma ln in Excel that also can be used to calculate this same thing actually. So, let me once more repeat, we have the mean time to failure is given by this formula. So, we can neglect this gamma if you want to have a 2 parameter variable. So, this is eta, as I said is nothing but scale, and beta is the shape. Eta is the scale and beta is the shape, okay. This is the shape, this is the scale. So, in our problem scale is given by 2000 hours, shape is given by 0.5. So, what do you do? You take 2000 here, gamma function of 1 by 0.5 plus 1. So, that will become gamma function of 3, and gamma function of 3 is given by 2 factorial, that is 2, and your scale is 2000. So, 2000 into 2, that will give you 4000 hours. So, the mean time to failure is 4000 hours. So, do you understand? And as I said, there is a command also called gamma ln, which can also be used in Excel combination. When you combine it, exponent of gamma ln, you will get the same answer. So, in this particular problem we are trying to look at probability that the artificial valve will last more than 4000 hours, and as you can see here, probability that artificial valve will fail less than 4000 hours will be 75%. So, 1 minus at 75% will be about 24.3%, okay. And then mean time to failure, we used this particular equation, we remove this gamma, call it 0. So, we have the scale factor and we have the shape factor. So, the scale factor is given by 2000 hours, shape factor is given by 0.5. So, we say 2000 multiplied by gamma of gamma function of 1 plus 1 by 0.5, okay, and the gamma function of 3 is 2 factorial. So, 2002, that is the 4000 hours is the mean MTTF, mean time to failure, okay. So, you understand how to go about doing this type of problems. They are quite useful actually to address, okay, do not forget that. So, in the Excel also we can do using this Weibull, but Weibull Excel cannot do the MTTF type of calculation. So, for MTTF we can combine the 2 commands exp and gamma ln together to get the MTTF, but it is not very difficult to do the MTTF because by using this table the gamma function of various numbers are given. Gamma of 1 is 1, gamma function of 2 is 1, gamma function of 3 is 2, gamma function of 4 is 6, and so on actually. So, it is very simple and straightforward for you to look at the mean time to failure, okay, and also to calculate probability that the artificial valve will last for more than 4000 hours, okay. So, as you can see, it is a very useful type of distribution which can be applied to many different situations actually. Okay, now let us proceed. You have these 3 parameters. We have the scale parameter, the shape parameter, and also the other third small gamma parameter. How do you estimate all this? There are different approaches by which you can estimate. One is called the probability plotting, other is called the rank regression or least square approach, maximum likelihood estimation, Bayesian estimation methods, and so many methods are there, but this is the most simplest, probability plotting. It is least mathematically intensive method for parameter estimation, okay. Okay, it is quite simple and it tries to linearize this function and then it tries to calculate. So, from the data, how do I calculate the scale parameter and the shape parameter? That is the question actually. So, there are this particular approach by which one could do that. So, if you have the 2 parameter variable, then we can calculate the unreliability matrix. Okay. What is unreliability matrix? 1 minus that is called the unreliability matrix. Okay. As I mentioned before, that 1 minus is so if you have the reliability e power t by eta raised to the power beta. So, 1 minus of that is called the unreliability matrix. So, this can be linearized. Okay. So, if I linearize this, all of you know how to linearize this, you end up with the term like this. Okay. Beta ln t minus beta eta ln of 1 by 1 minus qt. So, qt is this unreliability matrix 1 minus e minus t by eta raised to the power beta. Now, this looks like a y is equal to mx plus b type of equation where your x is equal to time. So, if I have data of qt versus t, all I have to do is plot this versus this, and the slope will give me plot this versus ln t, do not forget the slope will give me beta, okay, and the intercept should give me the other one, the minus beta eta. That is how you do it. So, we have the unreliability data qt as a function of time. We calculate this by taking 1 by 1 minus qt ln, then again ln, and then plot that against logarithm of t, and the slope should give you beta, and intercept should give you this particular term. Okay. So, that is another approach by which we can calculate these parameters in the model. Okay. Let us look at some problems actually later on as we go along. Okay. So, because nothing like doing problems which give you a lot of ideas about how to go about. Okay. So, we can determine by plotting these or the unreliability values, okay, and then we can achieve this type of calculations and results actually. Okay. So, we will continue more in the next class of thank you very much for your time.